Thank you all so much for coming and welcome to today's webinar on the potential role of hydrogen in the decarbonization of energy. Today we are joined by Andrew Gunning, Managing Director of IES Ltd, a medium-sized environmental consultancy based in Sheffield and with a regional network of offices throughout the UK. As a chartered engineer and chartered geologist, Andrew has extensive experience in environmental risk management in the energy sector, including hydrogen and natural gas storage. Previous experience includes also leading the groundwater component of the SHEAR project, a Horizon 2020 assessment of environmental risk in shale gas development. Andrew is currently working on risk management aspects of the NERC Equip for Risk project. Other experience includes the mitigation of legacy impacts from coal mining. So today, Andrew will share a brief review of the potential role of hydrogen in the decarbonization of energy and an overview of the issues related to the geological storage of hydrogen. As always, there'll be a chance for questions at the end of the presentation, so please do submit these in the Q&A button at the bottom of your screen at any point during the presentation, and then at the end, I'll ask those on your behalf. So again, if you have them throughout the presentation, just pop them into the Q&A box for us. And if you want to just add any comments or want to introduce yourself, you're welcome to use the chat box on the side of your screen as well. So thank you again so much for logging in, and I'll hand over to Andrew.
Good afternoon, everybody. Thank you, Catherine, for that introduction, and thank you for the invitation to address the IES. As Catherine said, I'm Managing Director of a company called IES. I'll just very quickly say a couple of words about IES. So we're a spin-off from the University of Sheffield some 30 years ago, still headquartered in Sheffield, but with a growing regional presence, expanding across several offices throughout the UK, from Scotland down to Cardiff, and 7 or 8 offices in England. We're a 100-strong team of specialists, and the areas that we operate in are energy and risk, environmental planning, ecology, arboriculture, heritage and archaeology, landscape, habitats creation, and water and environment. And our largest service offering at the moment is in ecology, but our strength is the ability to provide a multidisciplinary one-stop shop in all the services that we operate. The sectors that we cover range from infrastructure through to government, local government, national government, utilities, and local authorities. So, what is hydrogen, and how is it used today? So hydrogen is actually the most abundant element in nature, and it exists as a gas at very low densities. It is used in industry, and the global demand for hydrogen is currently 70 million tons per annum, and it's used primarily in oil refining and chemical production. It does have a fairly heavy footprint in terms of CO2 as it's used at the moment. And the value chain in terms of how hydrogen is produced and used ranges from dedicated production from natural gas, from hydrocarbons essentially, natural gas, coal, oil, and also as a byproduct of industrial processes. And it's used in refining, in a variety of other techniques, such as the production of methanol, iron production, and increasingly as a source of low carbon heat. So how can hydrogen help tackle the climate crisis? So I think low carbon hydrogen can be produced from renewables, which is green hydrogen, and blue hydrogen can be developed from fossil fuels. So just looking at the flow chart on the left there, you can see that blue hydrogen is created by steam reforming of natural gas, methane, and from that is produced hydrogen and CO2. So the CO2 will, in several schemes, which I'll briefly mention in a few moments, goes off to carbon capture and underground storage, whereas the hydrogen is then taken out and removed for use in transport industry power. Green hydrogen is produced by electrolysis associated with renewable electricity generally, and is used as a form of storing energy and then transported to the same sort of applications as blue hydrogen, but with a much lower CO2 footprint. So that is the, just moving on to the next slide. In terms of the interest in hydrogen as an alternative source of fuel, and potentially as ultimately a very low carbon source of fuel, there is considerable momentum developing across a number of countries which are regularly announcing roadmaps for hydrogen deployment. This is particularly taking place in Japan, in Germany, South Korea, Austria, France, across the European Commission and within the UN. And just as an example of that level of interest, in 2019, the Hydrogen Initiative was launched at the 10th Clean Energy Ministerial meeting in Vancouver, and that's co-led by a number of different countries and aims to produce international collaboration for commercial deployment of hydrogen. And at the same time, interest in Japan, the European Commission, the US has resulted in cooperation on hydrogen and fuel cell technology, much of which feeds into academic and industrial research projects. So there's an increasing level of interest in hydrogen. One case study, which is I find particularly interesting, is relates to Japan. So Japan, in terms of its energy mix, is very interesting. It has absolutely zero hydrocarbon resources, and it has, over the last 30 years, imported natural gas from the US and Russia, and it in fact developed the techniques to do that in the form of liquefied natural gas tankers, LNG tankers, which transport hydrocarbon gas, methane from into Japan. Japan's also relied heavily on nuclear technology, but following sad events several years ago, that's been on the decline. So hydrogen's one of the options that's being extensively considered by the Japanese. Indeed, they've developed the first liquefied hydrogen carrier, which a photograph of which is there, which is was launched earlier this year. It's aiming to supply Japan with hydrogen taken from coal seams in Australia, where the CO2 resulting from the process of the production is dispatched into depleted oil and gas reservoirs, and the hydrogen is transported to Japan, where it will be used in a variety of applications, including fuel cell vehicles, which the Japanese have a very ambitious plan and a network of hydrogen fueling stations to accompany that. So there's a number of different companies and government support in Japan. And one interesting thing is that the Olympic Village, which is, as you will know, the Olympics kick off later this month, and in Tokyo, the 2020 Olympics taking place in 2021. And the Olympic Village in Tokyo is entirely powered by hydrogen, and the transport is provided by hydrogen buses. Indeed, the Olympic cauldron is lit by hydrogen. So I think that just demonstrates the significance that the Japanese government is putting in hydrogen as a potential future clean energy source. So that's the sort of international picture. Coming back to the UK, as no doubt many of you will be aware, in 2019, the UK government committed to a net zero greenhouse gas emission target by 2050, and in Scotland that's 2045. So the UK energy industry is looking at means of achieving these targets, the decarbonisation targets, particularly of heating, power and transport. And as part of that investigation, hydrogen is what, particularly working alongside carbon capture, underground storage is one very serious element. And there are 4 projects which are being investigated in the UK at the moment. One is HyNet in the northwest of England, which is based around producing storage in the Liverpool-Manchester area, and developing an industrial cluster which uses hydrogen as a fuel source. H21 in the north of England is a design project which is looking at decarbonising the heating sector in northern England. Zero Carbon Humber is a similar project based around decarbonising the Humber region and developing an industrial cluster. And in Scotland, the Acorn project is an active development where it's associated with the bringing natural gas from the northern North Sea to the St. Fergus processing facility, where hydrogen is created alongside CO2. The CO2 is dispatched to a depleted gas reservoir, the Goldeneye reservoir in the North Sea, and the hydrogen transported to gas, blended into the gas network alongside methane. So a number of developments taking place in relation to hydrogen, and indeed the UK government is reportedly about to launch its hydrogen strategy this month. It's been in the pipeline for several weeks now, and there's reportedly it will be published in July. So I think that'll be a very interesting step forward in terms of the application of hydrogen in the UK energy mix. So that is a brief overview of the place hydrogen can have in the decarbonisation of energy. One of the key components in terms of that decarbonisation process using hydrogen is storage of hydrogen. A hydrogen economy needs a large storage requirement. That's both to deal with seasonality and demand, for instance, in heat networks, but also in security of supply, both of which are crucial to have an effective system. So in terms of methods of storing hydrogen, it can be stored as a gas, compressed as a gas. It can be further compression, can take it to the liquid stage. It can also be stored adsorbed onto solids and absorbed within metal hybrids and chemical hybrids, such as ammonia. And this diagram just illustrates the number of components that process can take, some of which are reversible, so that the hydrogen can be put into storage and brought back out. But for large-scale use of hydrogen for instance, in utilities, it's important to have something such as underground storage to allow for large volumes to be kept for seasonal storage and for diurnal storage. So in relation to that, some of the key properties around hydrogen just need to be considered. One of these is that at normal temperatures and pressures, hydrogen has a very low density, as you can see the numbers there. So that requires considerable reduction, and in terms of storage, the process there is that the gas will need to be condensed, put into storage, and then retrieved from storage and brought back to a usable compression ratio. So there's some specific properties around gaseous hydrogen which present unique challenges for geological storage. So it's a much smaller molecule, say, than methane, which makes it more transportable. It also has a very bad effect on steel pipelines, embrittlement, which is a major problem to be able to overcome. And also it can react with bacteria in storage reservoirs to produce methane, which effectively depletes the amount of volume we've got of hydrogen. So there are challenges. However, worldwide, there's a very well-established track record in underground gas storage generally. Natural gas has been stored routinely for decades, and predominantly that is carried out in depleted gas reservoirs, offshore gas reservoirs. The underground storage of carbon dioxide is increasing. 2019, there were 21 CCS facilities in operation. Some of those are linked to enhanced oil recovery. Others, such as the project in Norway, have been driven by fiscal policy, and that the Sleipner field has been in operation for over 20 years. So there is a body of experience which is developing there. The underground storage of hydrogen is comparatively rare at the moment, but there are locations in the UK and in the States where it's been in practice for a number of years, and in the UK for several decades. So UK underground gas storage experience relates to natural gas, carbon dioxide, hydrogen. So the differences here are that in natural gas is required to be injected and withdrawn from its storage facility. There are 9 underground operational gas stores in the UK. Primarily it's used for domestic consumption, heating, power generation. Carbon dioxide, which is basically removing CO2 from the atmosphere, is an increasingly important topic, and there are 21 operational CO2 storage sites worldwide, and 6 in development in the UK. And with carbon dioxide, it's a one-way trip for the gas. It goes into these long-term storage facilities, and it is designed so that it stays there. For hydrogen, it'd be similar to natural gas. The gas will be injected, stored, and then withdrawn. It's primarily at the moment used for ammonia production, but that provides a track record, which means that there is an increasing body of experience about hydrogen safely. And indeed in the UK, as I'll come on to, there are 2 storage facilities, both using salt caverns. So in terms of the geological hazards related to subsurface storage, it's been studied quite extensively now. In the HSE, Health and Safety Executive actually brought out a document in 2008 documenting the aspects which should be considered in underground gas storage. Fortunately, in the UK, one of the major risks which is associated with seismics is relatively benign, because seismic risk in the UK is low. But there are some specific geological risks related to storage which need to be investigated, and I'll come on to those briefly in a minute. I think the encouraging thing is that there's an increasing body of evidence that the mitigation of technical risks are well understood for natural gas and for CO2. And whilst there needs to be further work in relation to hydrogen, that track record can be directly translated. So, and many of the lessons that have been learned in relation to natural gas and CO2 are equally applicable to the underground storage of hydrogen. In terms of storing hydrogen, there are 3 options for large-scale underground storage, and they are depleted oil and gas reservoirs, or depleted gas reservoirs, I should say, not oil, saline aquifers, and salt domes, salt aquifers. They cater for different volumes. Depleted gas reservoirs and saline aquifers can deal with very large volumes, millions of meters cubed, many millions of meters cubed, at compressions, at very high compression rates. In addition to seasonal storage, there's also a need for lower volumes to be stored diurnally, and in that case, salt caverns provide, and other forms of surface storage provide options. I'll just talk briefly through the three major categories of large volume storage. And the first one of these being depleted gas reservoirs. This provides large storage capacity. And one of the key things is that the infrastructure is already in place, and the reservoir characteristics of the depleted gas reservoir are well understood. So that is a real bonus in terms of being able to store hydrogen within these depleted gas reservoirs safely and at relatively lower cost. And that lower cost is in comparison to saline aquifers, which are basically aquifers where there have been no hydrocarbons encountered. So they do provide very large storage capacities. In terms of immediate economic development, they require much more investigation. So there's higher cost in developing saline aquifers compared to depleted gas reservoirs, but equally they do offer very large potential volumes of storage. There is some track record of a saline aquifer, an onshore saline aquifer actually, which was in operation in France. This did encounter a number of problems, but it provides evidence of some of the issues which need to be overcome in relation to saline aquifers. The third method, which is generally caters for smaller volumes, is salt caverns, but this is a highly secure method of hydrogen storage. Salt is extremely impermeable. It flows under pressure, but it has the ability to self-heal, so which means it is highly impermeable, and gas stored within salt caverns is in a very secure environment. There's decades of experience in hydrogen storage in salt caverns, both in the UK and the USA, and that characteristic of rock salt, which makes it inert, is very important in that there's no risk of biochemical or geochemical reactions affecting purity. The volumes are smaller, which is a disadvantage compared to, say, saline or depleted gas reservoirs. Within the UK, there are several potential locations, and those locations cover the salt deposits in the UK, which are on the northeast coast, in the Cheshire region, and also down in the southwest, where there are very thick halite salt deposits. There are operational salt cavern storage facilities currently in place in East Yorkshire, in Cheshire, and there's some very recent news that SSE and Equinor plan to store hydrogen at one of the northeast sites, and that they've advanced to the final investment decision on that, and the site could be operational in 2028. So coming back to saline aquifers, there are also a number of locations where hydrogen storage is quite possible, and these are focused around the southern North Sea, where there are a large number of investigations going on. These are primarily related to CO2, but there's been a number of papers recently demonstrating that they have equally can be adopted for hydrogen storage and integrated with onshore wind farm use. So there's a number of within that particular area, and also in the northern North Sea, there are options for the development of saline aquifers, possibly working alongside using similar sorts of techniques to the CO2 projects. The carbon dioxide projects, there are two that have advanced quite significantly and are currently at feed stage, front end engineering design stage. And so that demonstrates that there's considerable expenditure already going into the development of underground storage facilities in the UK. There are alternatives, of which one is ammonia. Ammonia can be used to store hydrogen very effectively. It's increasingly being looked at as an option because it's probably most suitable for smaller volumes of hydrogen compared to a very large scale storage. But it certainly has options, and in Qatar, there's large-scale ammonia tanks are being developed for storage of hydrogen, which and each tank can hold 500,000 tons. So it's an area which has been looked at very closely. Another option is liquid hydrogen, and I think it's fair to say the Japanese in the lead here. They've been developing tankers. They've also got 35 years of experience of storing liquid hydrogen onshore, which for industrial applications, which gives them quite a track record in compressing and storing that tank. And this fellow here can store up to 540 meters cubed of gas, and has been doing so for 2 decades, which provides considerable track record. Another option is liquefied organic hydrogen carriers, and that is another technique for storage, more recently developed, but provides considerable scope for further investigation. Just starting to wrap up now, 2 more slides to go. What I would say in terms of hydrogen storage and hydrogen development generally, project risks for developers include obviously the regulatory and consenting and permitting aspects, as with any large development. To mitigate these types of potential risks, early environmental baseline surveys are needed, and it's surprising how many projects get way beyond the feasibility stage without looking at the need for baseline surveys, in particular to support site selection and optioneering studies. Another risk around in terms of development of projects is that consenting timeframes can be very, very lengthy. Again, this all points to early engagement with regulators, with statutory consultees in determining key milestones and the requirements to which may become apparent from baseline studies to mitigate impacts to the schedule of development for these projects. There are a number of risks related to hydrogen storage which need to be addressed, but I think that the track record is developing where that becomes less of a challenge than maybe it was 10 to 15 years ago. But if you look at the high risks that may relate to hydrogen development, hydrogen storage, the political environment is one that needs to underpin the financial investments that are required to invest in the hydrogen economy. And technical and regulatory uncertainty, because it's such a new and evolving sector, is something that needs to be taken into account alongside the economic, commercial and financial risks with any new industry. In particular, one thing that may develop there is the supply chain capacity risks, where in developing hydrogen, in that some of the technologies will require very significant engineering capacity. Public perceptions need to be managed, and consents, as I mentioned, need to be looked at in terms of the overall timescale. Critically, for hydrogen projects moving forward, it would be the need for project delivery to be safe, to be efficient, and for moving what are large, innovative, and complex projects forward in a manner which is both safe and acceptable in terms of the policy and PR environment. So I'll wrap up on this point. Just for a brief summary. There's an increasing worldwide focus on hydrogen as a clean energy source. Large-scale use of hydrogen will require extensive storage, geological storage, to provide seasonal buffering and security of supply. There's big potential in the UK for the use of hydrogen to decarbonise energy networks such as heating. And as part of that, the regulatory environmental risks need to be considered very early in the project life cycle so that they can be factored into the development programme. So that's it. I hope you found that useful. Thank you very much for your time.
Amazing. Thank you so much, Andrew, for that wonderful presentation. So we have some time for questions now. If you guys have any, feel free to put them into the Q&A box at the bottom of your screen. But yeah, we already have a few, so I'll just get started. So the first one, I think you touched on this a bit, but they've asked, do you see hydrogen as a solution for heating or for transportation?
Both. It can provide very different sort of solutions, but it can provide both. And one of the fuel cell vehicles provide a mechanism of rely on hydrogen as the feedstock. They can be very efficient, and also the method of recharging them can be much more practical, I would argue, than possibly electric batteries. In terms of the heating network, absolutely is a strong developing case for that. Initially, one would imagine that there will be a blend of methane and hydrogen put into the heating networks, and that over time the methane will be removed, and you'll move to 100% hydrogen use as the safety case is developed.
So the next question is, what are the most likely options for the distribution of hydrogen from the centralized storage sites you've covered?
Well, there's a number. This is not an area of my expertise, but I'm aware there's a number of options that have been looked at. One is pipelines. Another one is road storage, and there's also marine tankers being developed as well. The transport of hydrogen by pipeline is perfectly feasible, and there are some hazards to be worked around, but there are a number of options for dealing with those. I don't think there are any unpresentable challenges there which are not cannot be overcome.
So the next one is, what do you think will be the biggest challenge to reaching the 2050 NZC target? How will we overcome this challenge?
Well, it's a very big question. I'm not sure that I can necessarily answer that. But personally, I think hydrogen has a big role to play in decarbonisation, and I think it will, alongside electrification, it will present big opportunities to achieve the decarbonisation targets. Personally, I think what's needed is a twin track or more approach, examining several different routes to achieving that decarbonisation target. I think that's all I would say on that point.
Wonderful. Okay, so the next one is, are there other ways of decarbonizing energy that have potential to be adopted, or is hydrogen the main method for the future?
Oh, yeah, undoubtedly there are other technologies. Yeah, I think the advantage of the hydrogen economy is that it provides a source of energy which can be used in industry, it can be used in heating, and it can be used in transport. So it is readily adoptable across a whole range of sectors, and it's also a form of energy that we're familiar with dealing with, and increasingly understand the risks very closely. I suppose one of the big alternatives is nuclear, and then the other is renewable energy in the form of wind, solar. I mean, they all play a part of the mix. I'm personally quite skeptical about nuclear, because every time we get to a stage where it starts to become significant, something goes wrong. So you can go back to 3 Mile Island, you can go back to Fukushima. There are a number of incidents, and indeed in the UK there was quite a big incident in the associated with Sellafield in the 1950s, which was a close call. So I think probably what's needed is a holistic look at all of the sources of energy. Undoubtedly, wind and solar can play a big role, but I think hydrogen has a part to play.
Wonderful. So I've seen a question here about whether or not this presentation was recorded. It is, and we'll be putting it on our YouTube channel as well as the website. So keep an eye on that. And if you don't see it for whatever reason, just email us and we'll send you the link. Okay. Wonderful. Well, we have more time for questions. If anyone has any others, just feel free to drop them into the chat or the Q&A box. I suppose just while we're waiting for more questions, do you want to talk a bit about what maybe the next step is if people are interested in this topic and want to kind of do something themselves as an individual? What could they do to kind of search more about hydrogen and the decarbonization of energy?
Well, it's absolutely astonishing the amount of literature which is coming through in relation to hydrogen as a fuel source, and in particular over the last 2 years, there's been a dramatic increase. If you want to find out more about hydrogen, I would recommend Google Alerts. And if you put hydrogen in there, you're going to be surprised at how much comes through. And that's something that I've been using for a while now, and I find it very useful just to keep informed of the key developments. I would also I think we should be keeping our eyes open for the government announcement related to the UK hydrogen strategy, which is, as I said, potentially due any day. And that will map out, I mean, there's been a number of sort of, I don't know whether they're leaks or just guesses as to what will be in it, but it will set forward a program of work which will lead to adopting a number of projects in the UK, which will play a major role in decarbonising industrial sectors.
Amazing. Okay, so we have another question here. On the mix needed for domestic use of hydrogen, you mentioned needing to mix this with methane. Why would this be needed, and what would the environmental impacts of this be? And they've said burning methane isn't the best, in brackets.
Well, but if in terms of creation of methane, it is obviously has higher emissions than hydrogen. I think the point is that it's a stepping stone. So I think if one went to a full use of hydrogen immediately, then in terms of the heating network, you would have 23 million gas boilers, which would be inoperable. by adopting a blend of hydrogen and methane, existing infrastructure can be used, and that includes modern pipelines that have been put in, in the last 5 years, plus the end products, which are increasingly being developed to be hydrogen ready, but they're not all there yet, and therefore there would need to be a process of adaptation for existing technology. So it's a case of what's achievable versus, the requirement to decarbonize.
Right. So, go ahead if you want to.
No, I've nothing to add to that.
The next one is, as we move away from carbon, how might taxes move from fossil fuel to hydrogen and renewables?
I really don't know. But I think what I would say is that the work that we've done in this area over the last 2 years has highlighted that to kickstart the hydrogen economy, the governments will need to provide fiscal incentives because there's considerable risk, and therefore to get organisations to take those risks, they need to have financial support in one form or another. So whether taxation how that would develop over the next 20 years or so, I couldn't tell you.
Perfect. So the next one is, do health and safety considerations pose any constraints or issues to the widespread application of hydrogen in transport?
They do, but I think you could argue that they're all resolvable in much the same way as the use of petrol is. Petrol is not a safe substance, and it's, as we all know, petrol or diesel is in just about every vehicle we've got, other than those that are powered by electric batteries. I think similar sorts of processes can be adopted to make hydrogen acceptable for use.
Amazing. Well, thank you all so much. I think that's all the time we have for questions today. And thank you once again, Andrew, for presenting. That was super informative, and I hope you all got a lot from it today. So that's it for us today, but thank you so much for logging in. I hope you did find it beneficial and informative. Don't forget to record your attendance at this webinar in the IES CPD tool. You can do this by logging into the members area. This webinar, like I said, has been recorded and will be made available on the IES website and YouTube channel. If you are watching this on YouTube, please do subscribe to our channel, like the video, and hit that notification bell so you'll get notified when we have new content. So thank you again, Andrew, once again, and to everyone who attended today. I hope you have a lovely rest of your afternoon, and thank you for watching.